When we're talking about the normal force, we're not just talking about it going straight up in the air. We're talking about it going perpendicular to the surface. So when I draw my incline here, my normal force now goes like that. Okay, my normal force goes perpendicular to my surface. Okay, it makes that right angle with my surface. Okay, the normal force has to go perpendicular. So it changes the way we look at it just a little bit. Our gravitational force, however, still always goes straight down. Always. Okay, it's not going to change the direction that it goes in comparison to the incline. Okay, so if I have my incline now, I'm looking at my normal force, which goes perpendicular, and my gravitational force, which goes straight down. Okay, so my F sub g would go like this. My F normal would look like that. Okay. So when we're looking at our incline, we kind of rotate our x-axis so that it runs along the incline. Okay, so my axis now runs along the incline. Okay, so when we're dealing with things on an incline, we shift our vision just a little bit so that the gravitational force is the only one that's at an angle. Okay, it's the only one now that's acting at an angle. And we're going to break it down here in just a second. Its components, the components of our gravitational force, have special names. And we're going to talk about those here in just a second. Okay, so when we work on an incline, we rotate our axis so that it's along the incline. And we do this so we don't have to work with a component for the normal force, a component for the frictional force, a component for the applied force, all that kind of stuff. We're only dealing with components for the gravitational force. Okay? So let's look at this object here on my incline. I've got, let's say, my gravitational force that looks like this, F sub g. I've got my normal force that goes perpendicular. If I have a frictional force here, where would that be applied to? Kind of upward, right? It's not going to look like this, right? My frictional force wouldn't go into the plane of my incline. It's going to go opposite of the motion, right? So frictional force always goes up the incline. Okay, and if I'm pushing it down the incline, if I have some sort of applied force, it would go like that. If I was pushing it up the incline, it would also go that direction. Okay? Okay, so since the force due to gravity now points straight down, we've got to work with the components of our force due to gravity. Okay, so let's draw what this looks like one more time here. And we'll look, these are our new names for our components of our gravitational force. Okay, so I want to draw them out first and then we'll talk about them. Our force due to gravity goes straight down, F sub g. And that's at an angle as compared to our axes, right? Here's our y-axis, here's our x-axis. Okay, so that force due to gravity acts at an angle. We've got to deal with the components now of that force. Okay, so what we're going to do is we're going to draw these components. You're going to draw one of the components straight down, and then we make a right angle to come to my force due to gravity. Okay, so it's important that you understand the hypotenuse of this component of this triangle is always F sub g. Okay, you don't make a right angle. Some people have the tendency to make it look like this. That doesn't work, right? The white triangle doesn't work. We don't want our right angle to be here. We want our right angle to be here on this side. Okay? F sub g is always the hypotenuse of this triangle. So, we've got our components broken down of our force due to gravity, and each of those components has a specific name. It has a specific name. So this force on the bottom right here runs parallel to the incline. So it's called force parallel. Not force 11. Those are parallel lines. Okay, force parallel. That's always the horizontal component of our incline. Force parallel. Because it runs parallel to the incline. the force that runs perpendicular to the incline looks just like this force. Right? Runs in the same direction, should be the same magnitude because our object's not coming off the incline at all, right? It's not moving up and down at all. So this force right here is called the normal force also. Okay? These two forces are equal to each other. Okay? Your book sometimes calls this force right here force perpendicular. Okay? I don't do that. I still call it the normal force because I know those two are equal. So that's an easy way for us to solve for the normal force is to find that component. Okay, does that make sense? Your book sometimes will label it as force perpendicular. So if you see that, find the perpendicular component of our gravitational force, that's what you're looking for. It's really the normal force. Make sense? Okay, so we've got two new forces here, parallel and normal or perpendicular. On our diagram here. So we've got a 10 kilogram box sliding on a frictionless incline. Incline makes 30 degrees with the horizontal. We're going to walk through all these steps. Our overall goal is to find the acceleration of our box. Okay, we want to find our horizontal acceleration. So I'm going to draw my diagram over here. And let's go ahead and label all of our forces first. Okay, so go ahead and get written down what you need and we'll look at our free body diagram here. All right, so first we've got our force due to gravity, F sub g. We've got to break that into components, so we make our components. And remember, the right angle always goes opposite of the hypotenuse side. The bottom side of this component triangle is called what? Good, force parallel. And then this side is called the normal force. Okay, we also display the normal force that's acting up, but you know those two lines are congruent, okay, or they're equal to each other. Let's see here. It's sliding down the incline, so we don't have any sort of applied force. Gravity is doing the work to slide that box down the incline. We're not pushing it. Gravity's doing all the work. It's frictionless, so do we have any other forces we need to identify here on our free body diagram? No, we've got all that we need, okay? So let's think about here. We're going to walk through each of our steps. First and foremost, we've got to find out what F sub g is equal to. We've got to find the hypotenuse of that triangle. Okay, how do we solve F sub g? Mass times gravity. Good. Mass times gravity. So we're going to take 10 times 9.8. That's going to give us an F sub g equal to 98 newtons. Okay, that 98 newtons is going to be the hypotenuse of our triangle. From there, you can go to breaking down that triangle, that gravitational force. Break that down into its components. So let's solve for the normal force, F sub n. Okay, if you draw your incline like this, F sub n will always be using cosine. Okay, always using cosine. And let's talk about where we put our angle here. So we've got our 30-degree angle that we know that our incline is at. So our angle really sits, let me move this out of the way. Our angle really sits right here, okay, which translates to it fitting right here in our gravitational triangle. Okay, so this angle right here in our gravitational triangle is always the same angle at which your incline is lifted. Okay, so whatever angle it tells us our incline is at, if we're sitting on a 25-degree incline, then 25 would go into this pocket right here. Since here is 30, we know they have a 30-degree angle there. Okay, so those two angles always are congruent to each other. So F sub n means we're always going to take sine, so we'll take 98, that's our F sub g, times, cosine, not sine, cosine of 30 degrees. I got 84.9, okay? And then for our parallel force, we're going to take 98 times sine of 30. And get a value of 49 newtons. Okay, so now that we've got all of our numbers that we need, we're going to solve for the horizontal acceleration, which means we need to look at our net force equation in the horizontal direction. So let's start looking at F net in the horizontal direction. How many horizontal forces do we have? Just one, right? What is it? Parallel, good. Parallel is acting horizontally. So even though it's down here removed from the center of our system, we still have to understand that it's working in the positive x direction. Okay, since we rerouted our axes to look like this, we rerouted our axes, we know that the positive direction is still here, negative, negative, positive. Okay, we just tilted our axes just a little bit. So the parallel force is still acting in the downward or in the positive direction. So that means F sub net in the x direction is going to be F parallel. Do we have anything opposing that? No, so you can put a minus 0 if you want. You can leave that out if you want. Okay, we know the value for force parallel because we solved for it, 49 newtons. And what can we substitute in for F net? Mass times acceleration. M times A. All right, and we know that our mass is equal to 10 kilograms. So that means our acceleration in this case is 4.9 meters per second squared. Now this is a mix of forces and kinematics, so you're going to need the kinematics equations eventually. All right, so these are all the steps we have to go through. I'm going to get our free body diagram drawn. Do we agree on the free body diagram? Missing anything? Any extras? No here. What does the 466 newtons tell us? Tells us F sub g, or force due to gravity, right? It tells us its weight. And weight is F sub g. So we know that F sub g is already equal to 466. Okay, that takes out a step for us. 466. Where does our angle go here? 33.3 degrees. Which angle does it fit in? Here or here? The top one. It fits under the top. Okay, so 33.3 degrees goes here. So I'm going to have to draw that in there. All right, let's go ahead and find both of those components. So our F parallel is equal to, it's always going to be equal to sine if you draw your diagram this way, which is 466 sine of 33.3 degrees. Make sure your calculator's in degrees, not radians. Okay. So our overall goal here is to be finding time, right? They gave us distance final. They gave us everything we need to solve for the acceleration of our object. Then we're going to use our kinematics to go back and solve for time. So we've still got to find the horizontal acceleration of our object. So that's our mini goal right now. And then we'll go back and use our kinematics equation to solve for time. Okay? So if we set up our F net equation in the x direction, we only have one force, right? Only F parallel. That means we're going to set mass times acceleration equal to 255.8. But we have to solve for our mass. And how do we solve for our mass from F sub g? We're going to divide by 9.8. So F sub g equals mass times gravity. They gave us F sub g equal to 466. We want to find our mass, so we're going to divide that by 9.8. And I got 47.6 for our mass. So then we can plug that in over here. 47.6 times A equals 255.8. And we get our acceleration equal to 5.37? Yeah? Okay. From there, we need to pull out our kinematics equations. So we've got our acceleration. We've got our distance final. Okay, because we assume that we're starting at the top of the incline, we're going to travel the whole distance. Okay, so we've got acceleration, we've got distance final. What's our initial velocity probably going to be? 0. So V sub O is equal to 0. Distance final, or x is equal to 8.45. We have an equation we can use. The second one, right? X equals x sub O plus VIT, 1/2 AT squared. Okay, x is 8.45, 0, 0, 1/2 5.37 t squared. So I got t equal to 1.77 seconds. Let's try one with friction now. Try one with friction. This just adds one more component to our problem. And where does our frictional force go here? Yeah. Up the incline, okay, because we're sliding down. When it says we're sliding, that means that it's starting on its own. We're not applying any sort of force to that object, okay? It's sliding on its own. So our overall goal here is going to be to find the horizontal acceleration. Okay, I think I'm going to walk you through some steps, but I forgot to click that all the way through. Acceleration of the box as it slides down the incline. That's our overall goal here. All right, so F sub g is equal to mass times gravity. That's going to be the hypotenuse of that gravitational triangle. Oh, oops, I'm one off. 196. Right. I plugged in 98 instead of 9.8. Okay, let's break down that triangle now. So F parallel is equal to 196 times sine of 50 degrees, because our angle that we get always fits right into this pocket here. The normal force is equal to 196 times cosine of 50 degrees. Now you can either solve for your frictional force ahead of time, you can wait and plug it all in at one time if you want, that's totally up to you, okay? But if we solve for our frictional force, we're going to take the coefficient times the normal force, which is equal to 0.4 times 126. Which is equal to 50.4 newtons. Okay, and you could wait and plug that step in your net force equation. That's totally up to you. Okay, so let's look at our net force equation in the x direction. Matt, can you give me our net force equation? Perfect. F parallel minus F friction. Good. We're going to substitute MA right here Force parallel we solved to equal 150.1. Frictional force we solved to be 50.4. Our mass is 20. .99 meters per second squared, or 5 meters per second squared.